Well Labs with Brihad Bengaluru Mahanagara Palike and Friends of Lakes have co-created a framework for lake rejuvenation with the support of DCB Bank. This is the first version. The process of lake rejuvenation involves 5 stages: diagnosis and visioning, design, implementation, operations and maintenance, and monitoring and evaluation. In this video, we will elaborate on the second stage of lake rejuvenation, design. This video involves technical explanations. So please check out our first video that introduces the framework on lake rejuvenation and explains lake visioning. The video link is in the description.
The first stage of the lake rejuvenation framework was diagnosis and visioning, where we defined the lake's desired function by merging scientific knowledge with community aspirations. In the design stage, we focus on two key aspects. First, lake characteristics such as water flows, self-purification processes, and the aquatic life it supports. Second, we design build assets that can be introduced to enhance the functionality of the lake. Before starting the design phase, we need to understand various lake characteristics that influence its capacity to perform a target function, and then establish a baseline, which is a set of measurements reflecting the lake's current state. All the future progresses will be assessed against this data. Using the baseline, we then create an asset list to determine the essential assets required for the lake to function properly. In the next step, we identify design considerations to ensure that these assets are appropriately designed. Next, we assess the current condition of the existing assets to document the necessary changes required. Finally, we compile all this information into a detailed project report, which becomes the blueprint to guide the next stage, which is implementation. In order to establish a baseline, we consider three themes relevant to lake systems and processes: lake hydrology, lake biology, and chemistry. Generally, malfunctioning processes in one or more of these themes hamper the lake's ability to perform its desired function. For lake hydrology, we seek to answer questions such as: does the lake receive inflow throughout the year? Can the lake temporarily hold water during an extreme rainfall event to prevent damages to its surroundings?
Similarly, for lake biology, we identify the flora and fauna present in and around the lake and assess their habitat use to determine whether the lake is appropriately zoned based on its function, if filling supports macrophyte growth, and if the lake provides nesting and roosting sites for birds and amphibians. Finally, for lake chemistry, catchment characteristics along with in-lake water and sediment quality are surveyed to determine what is entering the lake and how it affects the lake's ability to perform its functions, as well as what is being retained and its impact on the lake's performance.
To address these questions, we conduct several key surveys. Reconnaissance survey is a preliminary assessment to document the lake's condition and key details. Topographical survey maps the lake's shape and surrounding landscape. Bathymetry survey measures the depth and contours of the lake bed. Hydrological measurements monitors the inflows, outflows, and seasonal water level changes. And GIS analysis, which examines the catchment characteristics, including upstream and downstream influences. By integrating these insights, we ensure a well-informed approach to designing and restoring a lake.
Now, all of these studies together help us understand the lake's current health and also what's going wrong. Under lake hydrology, we are interested in various water levels within the lake, as well as its storage and recharge capacities. A lake's water level changes with seasons. Now, these fluctuations are crucial because they help with flood control, groundwater recharge, and even the lake's long-term health. But what's currently going wrong? Many lakes now receive continuous inflows from treated and untreated wastewater, which prevents them from emptying or filling up naturally. On top of that, poorly designed assets like inlets, outlets, and storage structures, either placed at the wrong location or with the wrong capacity, further disrupt natural water flow patterns. In order to address these, we propose designing assets particular for flow regulation, such as sluice gates and weirs.
Regarding lake chemistry, we are interested in the different types of flows entering the lake and the corresponding pollutant load they carry. A variety of inflows enter our lakes. While some flows, such as untreated black and grey water, septic tank effluent, and treated water, can be continuous in nature, others, such as surface runoff, Sewer overflows during storm events and overflow from upstream lakes are dependent on rain events. Lakes have the capacity to break down pollutants from both external and internal sources. However, when excessive pollutants such as sewage or nutrients like nitrogen and phosphorus enter the lake, this capacity to assimilate is exceeded. This leads to algal blooms, murky water, and declining water quality, making the lake unusable for both people and aquatic species. To ensure the lake can effectively perform its target function, its water quality should meet the prescribed standards. To achieve this, we propose introducing water quality improvement assets either within the lake itself or in its surrounding area. When both options are unviable, we propose intercepting and diverting the incoming wastewater to a sewage treatment plant. Finally, lake biology is an aspect affected by both lake hydrology and chemistry. Aquatic plants and animals depend on seasonal water level changes for their life cycles. However, many lakes remain permanently full due to continuous inflows disrupting these natural cycles. In some cases, even the shape of the lake bed has been altered in ways that prevent habitats from forming properly. Similarly, the nutrients in the lake water column help nourish a variety of flora and fauna. However, excessive nutrients lead to decreased levels of dissolved oxygen required for their survival, resulting in eutrophication. To address these issues, the design of lake assets such as sedimentation ponds and treatment wetlands in and around the lake and sewage treatment plants at the catchment level is proposed. This approach captures untreated sewage before it enters lakes, preventing contamination and protecting aquatic ecosystems and public health. Additionally, creating habitats specific to observed lake-dependent aquatic species is also proposed to manage these issues.
How do we design lakes correctly? It's not a one-size-fits-all approach. Location, soil conditions, and peak flow all determine how assets should be placed and sized. When we combine scientific knowledge with design, we are not just restoring lakes, we are ensuring that they function properly for the long run. However, good design alone isn't enough.
Other important steps in the framework include implementation, where we verify the assets are constructed according to the design, operations and maintenance, where we ensure that the asset is operated at the desired level, and finally, monitoring and evaluation, where we provide a plan for both asset and lake characteristic monitoring to ensure that the target functions across the themes of lake hydrology, biology, and chemistry are met. If the functions remain unmet, we first trace the process back to ensure that the asset is being operated and maintained properly. If that's in order, we then check if the asset is designed correctly. If we find that that's also in place, then we need to assess whether the asset was implemented properly.
Thank you for watching this video. Click on the links in the description to read more about the framework.